Hello students and welcome to a new chapter about the reactions in aqueous solution. We're going to start by defining acids. The first definition of acids came by a scientist named Arrhenius. He decided that acids are substances that produces hydrogen cation or hydronium ion in water. Examples will be hydrochloric acid, nitric acid, sulfuric acid, and phosphoric acid. Here is an example. When we mix hydrogen chloride with water, hydrogen chloride will give a hydrogen cation that gets immediately associated with the water molecule and gives me hydronium ion. And also one of the outcome is the chloride ion. Now the hydronium ion is what we call a hydrated proton. So let me explain this part to you. Normally, a hydrogen cation is not found by itself. It cannot exist all by itself. It has to associate itself to something, and that something is the water. So if I add these two together, so we call a hydrogen cation proton for the simple reason that the hydrogen atom has one proton and an electron around it, and that's the hydrogen atom. If I want to make a hydrogen cation, then that electron has to go away, that has to be lost, and now this is a hydrogen cation. So a hydrogen cation is indeed one proton. That's why we call it a proton. So if I mix if I produce the hydrogen cation, it will immediately associate itself with a water, and that will give me hydronium ion, which is hydrated proton. So it's a proton in which it's hydrated by one molecule of water. This is just to simply explain all these terms to you. He also defined bases as substances that produce hydroxide anion in water, like sodium hydroxide, potassium hydroxide, barium hydroxide. Also, ammonia does fall into that category. Ammonia is an Arrhenius base because when I mix it in water, it will produce hydroxide ion. So it does, comply with the definition of Arrhenius base. As you can see in the example here, when ammonia was mixed with water, it gave at the end of the day the hydroxide anion, which is how Arrhenius defines bases. These definitions are limiting and only apply to aqueous solution. So it really did not cover all kind of acids. It only covers the ones that are in aqueous solution or in water. So then another scientist, Bronsted, identified acids and bases differently. He said that a Bronsted acid is any substance that donates a hydrogen cation or a proton. And in these substances, hydrogen normally is in the front when we write the formula. And a Bronsted base is any substance that does accept that proton. A monoprotic acid are acids that will yield only one proton once dissolved in water, like hydrogen chloride. It will give me only one proton, therefore it is a monoprotic acid. Acetic acid, it will only give one proton once dissolved in water, and therefore it will be a monoprotic acid. Diprotic acid, each unit will give two protons, like sulfuric acid, for example. And triprotic acid, each unit will give three protons, like phosphoric acid. Now we're going to look at some acid-base reactions. Neutralization is the most common reaction, which occurs when a hydrogen cation or a proton and a hydroxide anion combine together to form water. So here is an example. Hydrochloric acid react with sodium hydroxide solution to give me sodium chloride and water. So acids react with bases to give me salts and water. Salt is defined as any ionic compound, however, unless it has a hydrogen cation, hydroxide, anion, or oxide, that will not be salt because these characteristics will make them either acids or bases. A Bronsted reaction is when we transfer a proton. So let's look at this reaction together. Ammonia react with hydrofluoric acid to give ammonium, aqueous, and fluoride anion. If I'm going to follow Bronsted definition, ammonia did accept the proton and hydrofluoric acid did donate the proton to ammonia in the forward direction. Therefore, in the forward direction, this substance acted as the acid and this substance acted as a base. However, if you look here, you can find that this reaction is an equilibrium, which means it goes both way, forward and reverse. So when it comes in the reverse direction, I'm going to change the color. If I'm looking at the reaction this way, then fluoride did accept the proton that ammonia donated in the reverse direction. So in the reverse direction, fluoride acted as the base and ammonium cation acted as the Bronsted acid. Reactions of acids. Acids react with some metals to produce hydrogen gas in what we call single replacements reaction, as you have seen before. So hydrochloric acid react with magnesium to give me magnesium chloride and hydrogen gas. To remind you guys, this is a single replacement reaction in which hydrogen was replaced by magnesium and hydrogen chloride to give me magnesium chloride. So hydrogen has to leave, and it leaves in a form of a gas. It reacts with carbonate and bicarbonate to produce carbon dioxide. So here is an example. Hydrochloric acid reacts with calcium carbonate to give me calcium chloride, carbon dioxide, and water. Now again, guys, this is actually a double replacement reaction, so I don't want you to get confused about this. This here, calcium replaced hydrogen in hydrogen chloride, and hydrogen replaced calcium in calcium chloride. So if I am writing a double replacement reaction, I'm going to say calcium chloride and carbonic acid. However, carbonic acid in water does decompose to give me water and carbon dioxide, and this is where these two are coming, right? That's the decomposition of carbonic acid. This does summarize what I needed to talk about when it comes to the definitions of acids and bases, whether it is Arrhenius acid and base or a Bronsted acid and base, and some of their reaction. I will see you next in the molarity, dilution, and solution stoichiometry lecture.